In this unit, we've been discussing solid, liquid, and gas. Solid and liquid, they're able to stay within that particular phase because of an intermolecular forces. The three types are hydrogen bonding, dipole-dipole, and London dispersion forces. These three types of intermolecular forces are in between the two different molecules. So like this water, and that dashed line represents the intermolecular force. In a solid state, there is a lot of intermolecular forces taking place, a little less in the liquid, and very little or none in the gas phase. Our focus, therefore, in this intermolecular forces are based off of solid and liquid phase. Now, this particular video will focus on the London dispersion forces. Let me begin by illustrating London dispersion forces with chlorine molecules. So here I have chlorine gas. This is one gas and this is another one. Well, there's a particular moment. It's a random moment in time in which all of the electrons within the chlorine just kind of shifts to one side. Remember, this is random. It's not induced. So electrons are all happen to come in on one side, and this electron on this chlorine happens to go on that side, creating more of exposure to the proton of the chlorine, and that exposes positive charge of the chlorine on the other side. That creates this cloud of partial negative charge and cloud of partial positive charge on the opposite end of the pole, creating this almost like a very weak dipole moment. What this causes the next chlorine molecule to do is that these negative charge electron pushes some of the electrons here, and then this will also experience electrons to go from one area or multiple areas to more shift to one area, like this. That also exposes the positive protons within the nucleus and then creating this positive charge pole. So there is, again, a cloud of partially positive on one side and partially negative on the other side. Chlorines are nonpolar, meaning that there is an equal pull on each side. So even though this is a nonpolar molecule, there is it creates a small dipole moment wherein it's which one area is partially positive and partially negative. This is fairly weak. This can also happen to water molecule, which is a polar molecule, and not based off hydrogen bonding, but rather because there's just shift in the electron just at a brief moment where all the electrons are all spending its time on one side, exposing the other in the proton, causing a partially positive on the other side. The interaction between the two are this partially negative and positive. This is London dispersion. This could happen to some other polar molecule like HCl as well. So the interaction right here in between, this is where the London dispersion forces is happening. I'm going to abbreviate it as LDF. LDF. Again, it is an interaction between partially positive, partially negative poles of the entire molecule. All types of molecule, whether it's polar or nonpolar, will be involved in London dispersion forces. Now you might ask, well, this one has hydrogen bonding and this one has dipole-dipole. Yes, that is true. This has hydrogen bonding, but in addition, it has London dispersion forces. In addition to dipole-dipole of the HCl, it will have London dispersion forces. So let's give a good definition for London dispersion forces, and they are the attraction between two molecules when dipole of the one molecule creates the dipole of another molecule. It's creating the dipole. And the strength of this intermolecular forces is pretty weak. So out of the three, let me go back real quick. Out of the three that's here, this will be London dispersion forces will be the weakest, strongest, then second, and then the weakest. All right, let's move on. Now, as the London dispersion forces as the non-polar molecule goes from solid, liquid, and gas, there comes a breakage of the London dispersion forces little by little. So from solid to liquid, you can see there's a phase change occurring and the London dispersion force break. Going from solid to liquid, this is considered to be a melting point, the temperature in which it goes from solid to liquid, and there has been some breakage of the London dispersion forces. Then further from going from liquid to gas, this is where boiling point is or boiling temperature is, and that's going from liquid to gas, and there is very little or none of the London dispersion forces occurring because they're far from each other. Now let's compare these three states. These three states. So this one involves in hydrogen bonding and London dispersion forces, this water. It's hydrogen bonding and LDF. This one, HCl, experiences both dipole-dipole and LDF. And lastly, this chlorine molecule only experiences London dispersion forces. Now, generally, the water will have a higher melting point than HCl, meaning to get the temperature going from solid to liquid for water, it requires more heat than comparison to this one. That's because the breakage of here is much easier than over here. And that applies for boiling point. Going from liquid to gas, this one generates a higher boiling point, higher temperature required to boil. Generally, molecules with higher hydrogen bonding will have a higher boiling point and higher melting point. Okay, how about comparing the dipole-dipole HCl with chlorine gas? So this one will have a higher melting point than this one. And for the boiling point, this one will have a higher boiling point than this one. And that's because the dipole-dipole is a greater in attraction comparison to the London dispersion forces. So generally, you can say the dipole-dipole bonds have a higher melting and boiling point than comparison to something that has only London dispersion forces. So let's organize everything to determine what intermolecular forces is actually molecule involved. So I'm going to go ahead and show you a chart here, and you're going to read this chart, and I'll go one by one to determine whether a molecule experiences hydrogen bonding, dipole-dipole, or London dispersion, or two of the above, or maybe all three. How do we know? Let's do HBr. So here is H and then Br. What intermolecular forces are involved? So you're going to look at this. Is the molecule polar or non-polar? I can tell this is a polar molecule. It's probably going to have partial negative here, partial positive. So we know it's polar. So we go in polar. Okay, so is hydrogen directly attached to F, O, or N? Fluorine, oxygen, nitrogen. So none of those are applied here. So the answer is no. And so therefore this will experience dipole-dipole and London dispersion forces. Okay, so put this in mind, and we're going to do another example. Let's do H2S and CH4. Now, before you begin, I highly encourage you to draw the Lewis structure of the two. and then come back and check this video. And here is the key. Let's start off with this. This is a polar molecule, so let's go back. It is a polar molecule, and is it directly attached to F or N? No. So therefore, it's dipole-dipole and London dispersion forces. So this one is dipole-dipole and London dispersion forces. What about CH4? A little more challenging here. All hydrocarbons, so if they only have hydrogen and only carbon, we consider them to be nonpolar. Are nonpolar. Okay, so let me go back. So is a molecule polar or nonpolar? Nonpolar, so therefore just LDF. So LDF. Okay. Now comparing these two, can you tell which might have a greater boiling point? Hopefully you were able to say this one has the greater boiling point. So something with London dispersion forces only will have a less of a boiling point. Something that has dipole-dipole and London dispersion forces will have a greater boiling point. You're going to determine what type of intermolecular forces is or are in the following molecule compounds. Try this and come back and check. And here is the key. Next one, consider the compounds dimethyl ether, that's this one, ethanol, that's this one, and propane. Here's another one. Their boiling points are not necessarily in order. Are negative 42.1, negative 24.8, and 78.4. Match each compound with its boiling point. Now come back and try it and then check the key, and I'll explain a little bit. And here is the key. The reason why it's in this order, let's talk about the ethanol, the one with the highest boiling point. And why is it the highest boiling point? Note that this oxygen is attached to the hydrogen. That means that this molecule has the ability to do hydrogen bonding. And all molecules can do London dispersion forces and will do London dispersion forces. Something with a hydrogen bonding will have the greatest amount of boiling point. Next, let's look at this one. This is a polar molecule, but it is not considered to have hydrogen bonding because that hydrogen is not directly attached to the oxygen. It's a part. So this one is a polar molecule, but experiences dipole-dipole interaction, dipole, and London dispersion forces. Hence why it's the next one. Now this one is only made up of C and H. So it's a hydrocarbon. This is a non-polar molecule, so therefore it's going to have only London dispersion forces and have the lowest boiling point.